I hope you see the whiteboard and you hear me well, right?
Yeah, no problem.
Okay, great. So let me do the first thing. This is to correct a typo in a formula of the last lecture when we computed the limit of a point in our projective embedding x under the action of a multiplicative one-parameter subgroup. I mean this formula. So we computed this action in coordinates, and we got this line, this one. And after that, I said that since we consider projective coordinates, we can multiply them by one and the same scalar. And I multiplied all coordinates by t to the power L naught. And so these factors just vanish. We replace them just by these values. And here we get, we had before t to some minus li's to the power minus li's. And when we multiply by t to the L naught, then we get t to the difference powers, L naught minus L1, L naught minus L1 here, L naught minus L2 twice, and so on. L naught minus Ln, L naught minus Ln at the end. But it seems that in the lecture, I wrote these differences in an opposite way, L1 minus L naught, etc. So it was a wrong formula. But I corrected this formula in the notes. So you have this correct formula in the notes which are on the net disk. So in the notes, the formula is already correct, like here. And after that, since all these differences are positive because of this condition, we get that when t tends to 0, so these coordinates tends to 0 as well. And so all the reasoning after this line remains unchanged. So everything is correct except for this this line where I made correction in inverting the differences here, here, and here. Okay. So this was an update for the last lecture, and now let me turn to this lecture, to today's lecture. So as I promised, I turn now to the classification problem for spherical varieties. Classification of spherical varieties. And more precisely, I will address the second part of the classification problem. That is to classify spherical varieties containing a given spherical homogeneous space as the open orbit. I leave aside the problem of classifying spherical homogeneous spaces themselves. The problem which I address is the following one. So let Y, or maybe Y not, be a given spherical homogeneous space. So it is isomorphic to G mod H. It is a given spherical homogeneous space. So the problem is to classify spherical varieties, say X, containing this Y naught as the open G orbit. this is a problem I'm going to study. And let me say that the solution to this problem was obtained in a seminal paper of Luna and Wust first. Of 1983. And its presentation, yes?
Do we need the variety X to be projective?
No, no. Well, we assume normality. As I said sometimes before, we consider only normal spherical varieties. So I just skip this word normal here because we agreed to consider normal varieties, but not necessarily projective, any, in fact. Of course, projective will also be classified. As I said, this problem was solved by Luna and Wust, but the modern presentation, which I'm going to describe, is due to Knopp in his paper of 1991. Okay, so how do we handle this classification problem? We perform the classification in terms of certain invariants of geometric and combinatorial nature. You will see which kind of invariants we'll have. The point is that these invariants depend only on the open orbit in a spherical variety. In other words, they are the same for two birationally and equivariantly isomorphic spherical varieties. And for this reason, we call them birational invariants. So my first goal will be to introduce birational invariants of spherical varieties, or even of spherical homogeneous space, if you like, because they are birational. Birational invariants. So the first one of these invariants will be what is called the weight lattice. Weight lattice. What is it? So consider the natural action of the Borel subgroup of G on the function field of X. Or which is the same on the function field of the open orbit, why not? So the action of the Borel subgroup on the function field K of X or K of the open orbit, why not, which is the same. So this action, let me recall the formula for this action. So an element of B acts on a function F. We get a function whose value at the point x small is f of B inverse applied to x small. This is just the standard way how you get the action of a group on functions if you get if you have the action of a group on the underlying set on which these functions are defined. And we may consider the group of rational functions which are semi-invariant with respect to this action. Group of B semi-invariant rational functions. So what is this? Let us denote this group like this: K of X over B in brackets, in parentheses. So this is the set of all non-zero rational functions which are multiplied by a scalar under the action of the Borel subgroup. So this scalar, of course, depends on the acting element. So this is a character. So a function f is semi-invariant if the action of b on this function multiplies this function by a character, lambda of b. This is for any b small in big B. And for some character lambda in the character lattice of B, or of the maximal torus, which is the same. Okay. So
not for fixed lambda, right?
Well, I mean this lambda depends on f. So for any f, you have its own lambda. You consider all semi-invariant functions corresponding to different characters, not just to one and the fixed character, but to all characters. Okay? Well, as I already observed, why it is a group, by the way? Because it is a multiplicative subgroup in the multiplicative group of the function field. Because when you multiply semi-invariant functions, you get again a semi-invariant function, and its eigenweight, the characters just sum, just add. When you multiply functions, the character add. Let me again remark that this group depends only on the open orbit, because it is a birational invariant. It is defined in terms of the function field. So you may replace here x with the open orbit or with any other embedding of this open orbit. This guy will not change, essentially. So now what is the weight lattice? The weight lattice is just the weight, the set of all eigenweights of all semi-invariant functions contained in this group. Maybe let me write down the definition on the next page. So the weight lattice let me denote it lambda sub x. Well, of course, it is the same as lambda sub y naught. It is the set of all characters of the Borel subgroup occurring as eigenweights for some semi-invariant functions. So such lambda. Yes.
Sorry, I want to ask a question. You say that the B semi-invariant functions form a group, right?
Yes, under multiplication.
Yes, under multiplication, but I think multiplication of functions correspond to multiplication of characters, not the sum of.
You are right. You are right. Of course, you are right. But
in additional
remember,
form.
Remember that we write the character group in an additive way. So we write the multiplication of characters as addition. This is our convention. We want to view this group, this character group, as a lattice. So it is usual to consider the additive law in the lattice. Yeah, that's why we write this group additively. So you are right that when you multiply functions, you multiply characters, but we write this multiplication of characters as addition. This is our convention. Okay. Okay. So let me finish the definition of the weight lattice. So this lattice consists of all characters of the Borel subgroup occurring as eigenweights of some semi-invariant rational function. So such lambda such that there exists a semi-invariant function, say f sub lambda, of weight lambda. This weight lattice is a subgroup or sublattice, if you like, in the character lattice of B. But it may be smaller because maybe not any character of B may occur as a weight of some semi-invariant rational function on X. Why? So what is the reason for lambda to occur as a weight? Maybe some weights occur as some characters occur as weights, and the other do not. So this weight lattice is a sublattice in lambda of B. And also, let me make another remark, important remark, that this semi-invariant function f lambda corresponding to lambda is actually unique up to a scalar multiple. Unique up to a scalar multiple. Indeed, suppose we have two such functions of one and the same weight, lambda. Then, so why it is so? If you have another function, f lambda prime, of the same weight, then the ratio of f lambda over f lambda prime over f lambda is a B invariant function, because the numerator and denominator of this fraction have one and the same weight, and when you act by the Borel subgroup, these weights cancel each other. So the ratio is a B invariant function. And since our variety X is spherical, there are only constant functions which are B invariant. So this ratio is a constant. And so this f lambda is uniquely defined by lambda up to a scalar. You can reformulate this observation differently. In other words, we have an exact sequence of groups. Like the following. So 1 maps to K cross, maps to the group of semi-invariant functions, maps to the weight lattice, maps to 0. So the first two arrows are just embeddings, inclusions, and the third arrow from here to here sends a function f lambda to its eigenweight lambda. And by the above observation, the kernel of this map is exactly constant, the group of scalars, K cross. So we have this exact sequence. And by the way, this exact sequence splits because the target group is a lattice. Lambda sub x is a lattice. It is a free abelian group, and so you can lift this group to the middle term of this exact sequence. You can do it in an explicit way. Namely, if you choose, so you have this open orbit, y naught, and inside this y naught, you may choose y upper naught, the open Borel orbit, open B orbit. Because a spherical homogeneous space contains the open B orbit. And if we choose the base point, y naught, lying in this open B orbit, base point, then after the choice of this base point, you can choose the eigenfunctions, the semi-invariant functions f lambda in a canonical way. So you may choose f lambda so that f lambda, all f lambda take value 1 at this base point. Because f lambda, each f lambda nowhere vanishes on the open barrel orbit. When you act by B, the value is multiplied by a character. So if it vanishes at one point, it will vanish at all points. But then it will be identically zero. And this contradicts our assumption. We are considering non-zero rational functions. So a non-zero B semi-invariant rational function does not vanish at any point of the open B orbit. And therefore, we can normalize them in such a way that they take value 1 at the given point. And this gives you the lifting of this group to this bigger group of semi-invariant functions. So this exact sequence splits. Yeah, I mean, you may write under this convention that f lambda takes value 1 at the unity. So obviously you have that f lambda plus mu equals to f lambda then f lambda plus mu equals f lambda times f mu for any lambda mu in the weight lattice, and we have this splitting. And yet another notion, the rank of a spherical variety, let me denote it, R of X, is by definition the rank of the weight lattice of X. Okay, so these are basic notions about this first birational invariant of a spherical variety, or say homogeneous space, which is the weight lattice, and the rank, which is just the rank of this lattice. Maybe let me consider an example. If we take a generalized Fleck variety, that is x equal to g over p, g mod p, where p is a parabolic subgroup, an intermediate subgroup between the Borel and the whole group G. Then we may take the base point whose stabilizer is this P. So the stabilizer of the base point will be P. Then we have this Borel subgroup, which is contained in the stabilizer. But in this notation, it will be convenient to choose the opposite Borel subgroup, B minus, opposite to B. Since all Borel subgroups are conjugate, all the invariants which we are considering essentially do not change when we replace a Borel subgroup, a chosen Borel subgroup by its conjugate. All the invariants will be the same essentially.
Well,
so
the GY naught here is the stabilizer of Y naught, right?
Exactly, it is the stabilizer. So Y naught is in the subscript. It is somewhere below. This is the stabilizer. Stabilizer, let me write here, stabilizer. Okay. So if we choose for Borel the opposite Borel subgroup B minus, then the unipotent of B minus actually has the open orbit in X. The orbit, the U minus orbit of this point Y naught will be open in X. This is because we have this big cell, if you remember. So we have this big open subset B minus times B, which is the same as U minus times B, because B minus and B both contain the maximal torus T. And this is the open subset, big cell. And if we replace here B with P, we get even a bigger open subset. B minus times P, which is the same as U minus times P. It is the bigger open subset, even bigger open subset. And since this product set is open in G, this one, then it means when you take the quotient by P, by the right action of P here, you get that the U minus orbit of the base point will be open in X. So, we have this unipotent open orbit, and this means that the rank of X is 0, actually, because any semi-invariant function for any semi-invariant function on X, semi-invariant with respect to B minus, with respect to the opposite barrel subgroup, it is actually constant on the U minus orbit, because the character, the eigenweight of this F, the eigenweight of F, it is the character of B minus, but any character is identically one on the unipotent part, on unipotent elements. So this F takes one and the same value on all at all points of this U minus orbit. And this means that there are no semi-invariant functions, because this orbit is dense, open and dense, of course, by irreducibility. This means that there are no semi-invariant functions on the generalized flag variety except constants. In other words, the rank of X is 0. So generalized flag varieties are spherical homogeneous spaces of rank 0. In fact, this is a characterization.
The rank is the rank of the weight lattice, or the
exactly
rank?
It is the rank of the weight lattice. But since all semi-invariant functions are constant, this means that in this exact sequence, the right-hand side is 0. So this guy is 0. The weight lattice is 0, and this means that the rank is 0. Okay?
So you use the additive notion.
Yeah. When we speak about characters, we always use additive notation. Yeah. This is our convention for all times. Let me add that actually this equality is a characterization of generalized flag varieties. So you can prove, one can prove that if a spherical homogeneous space has rank 0, then it is isomorphic to a generalized flag variety. We'll see it later. Even sphericality is not essential in this statement, but let us do it for spherical homogeneous spaces. So the only spherical homogeneous spaces of rank 0 are, or if you like, the only spherical varieties of rank 0 are generalized flag varieties. Because this generalized flag variety is already projective. You cannot compactify it. You cannot add anything on the boundary. You have just a single embedding of this guy, this homogeneous space itself. So you may say that the only spherical varieties of rank 0 are generalized flag varieties. Okay? So now let me discuss the second birational invariant which appears in the classification. It is more complicated and more interesting. We may call it invariant valuations. So first, what is the evaluation? Let me give you a definition. evaluation of a function field of the function field of a variety x. Well, I will consider spherical varieties, but you can apply this definition to any reducible variety. Evaluation of this function field k of x over the field of constants k is by definition a map, say V, from the multiplicative group of this field, so all non-zero rational functions, to rational numbers satisfying the following properties. So such that first, this map is a group homomorphism, that is V of the product f times g is the sum V of f plus V of g. So the map V is a homomorphism from the multiplicative group of non-zero rational functions to the additive group of rational numbers. The second property explains the behavior of this map with respect to sums of functions. So the value of V at the sum of functions f plus g, well, we cannot say what it is explicitly, but we can say that it is at least greater or equal than the minimum of the values of V at f and at g.
Well, Professor.
Yes.
You mean the valuation is of kx over k, right?
Yes, yes. This is the definition. The definition
so
of what is it?
Of this valuation in Q, not in K.
Yeah. This map takes values in rational numbers.
So what does the over K mean?
You'll see it in a moment. You'll see it in a moment because I haven't finished the definition. There are only two conditions. There will be four conditions. But let me comment on the second condition. It may happen that f plus g equals to 0. Then the left-hand side is formally undefined because you define this map V only on non-zero functions. But we can take, formally you have to write here that this inequality holds if f plus g is non-zero. But you can extend the map V to the whole field of functions by assigning to the zero function. We may put, by definition, V of 0 equal to plus infinity. Of course, this is not a rational number, but you can formally add rational numbers and this sign. Of course, when you add plus infinity to anything, you again get plus infinity. So formally, under this convention, this inequality makes sense without any restriction on f and g. So even if f plus g equal to 0, then this inequality makes sense because it just says this plus infinity is greater than any other number. Of course, it is a natural convention to think. And also, the first condition will still hold if one of the functions, or maybe even two of these functions, are equal to infinity. Then we just get plus infinity here or here or here, but still the equality remains true. So formally, it is sometimes convenient. Sometimes it is convenient to adopt this condition, but you may also do without it. Then you have to make some restriction here. Well, this is the second condition. Now, the third condition, the third property, this answers your question, is that the evaluation V takes 0 values at constants. So V of K cross is 0. This is exactly what is meant when I say that it is evaluation of K of X over constants. So this field of constants is where the evaluation takes the 0 value. Okay? And finally, the fourth condition is that the image of the map phi, of the map V, excuse me, the image of the map V is a cyclic subgroup in Q. It is either isomorphic to Z or just 0. So any cyclic subgroup in Q, cyclic additive subgroup in Q, is either infinite or 0. This is my definition of the valuation of the function field over the field of constants. Well, it is not the more general definition of evaluation of a field, of course. If you know well, if you know commutative algebra well, then maybe you've come across more general definition of valuations. On the other side, there is a definition of a discrete valuation in which usually the value group, this group is taken to be Z, just integers. But it is not convenient for us to assume that the value group is integers, though essentially it is the case, because our fourth condition says that the value group is isomorphic to Z. It is a cyclic subgroup in here. But it is convenient for us to adopt some rational multiple. So it is Z, the value group is Z up to a rational multiple, the generator of this group. It will be convenient to use this definition, like we have given. This is the definition of evaluation. And also, let me give you an exercise. Maybe I even have some space to write it here. Let me write exercise, maybe here. Exercise 1. So this is about the second condition. You see that in the second condition, you can only say that you have an inequality. You cannot express the value at f plus g in terms of the values at f and at g. You can only write down an inequality here. But if these two values are different, if v of f and v of g are different numbers, then in fact this inequality turns out to be an equality. So prove that the equality holds in the condition 2. The equality, I mean, instead of the inequality here. The equality holds here in condition 2 if v of f is not equal to v of g. In this case, you can express the value of f plus g just to be the minimum of values of f, v of f and v of g. It is not hard to deduce from other properties and from this property just by definition. So it is an exercise for you. But it is important. It is an important addition to the property 2. So we shall use it. This was the definition of evaluation. But what is the main source for evaluations of functional fields? The main source for valuations is provided by prime divisors on normal varieties. So let me consider the basic example. Suppose you have a normal variety X. Well, we already assume X be normal, so I will not write it explicitly. And suppose we have a prime divisor D on X. Then we can associate to this prime divisor D, we can associate evaluation in the above sense. Let me denote it V sub D. By defining the value at the function f be the order, the vanishing order of f along D. So if f has a 0 along D, then it will be the order of 0. And if f has a pole at D, then it will be the order of the pole at D, of f at D, with the negative sign, with the minus sign. So the vanishing order of a function along a prime divisor gives you evaluation of the function field. For example, now let me give you a particular example. For example.
So
yes,
the order of f on D is the intersection of the singular focus of f and D.
Well, we have defined what is the order of f along a prime divisor on a normal variety. You have to restrict f to the regular locus, to the smooth locus. Okay. Well, so let me give you a basic, a particular example of this general situation as before. So suppose your x is just a projective line. X is P1. A divisor on a line is just a point. So let us take the infinity point at P1. Consider the function field k of P1, which is of course the same as the function field of the affine line, P1 without the infinity point. And it is a field of rational function in one variable, of rational functions in one variable, say t. So t is the affine coordinate on this affine line. And now, if we take any function, any f in this function field, then it can be expressed as the ratio of two polynomials, p over q, where pq are just polynomials in T, that is regular functions on the affine line, then the valuation corresponding to this infinity divisor, to this infinity point, which is a prime divisor on the projective line, the value at f equals, can you say equals to what? Any idea? Well, you have to look at the properties of the valuation.
Equal to the degree of Q.
Say it again, please. Can you repeat?
Oh, I think it is equal to the degree of Q.
Just degree of Q. So you mean it does not depend on P?
Oh.
Well, actually, of course.
If you if you are no, I think I got something wrong. It's the degree of Q minus the degree of P.
Absolutely, you are right. Degree of Q minus degree of P. So why so? Let me maybe make a step back. Because you have this first property. So when you multiply functions, the values of the valuation add. This means that if f is a ratio p over q, then the value at f is the difference of the value of p minus the value of q. Okay? And it remains to consider the case when f is a polynomial. So suppose, for instance, let's take q. What is the vanishing order of q, of the polynomial q at the infinity point? Of course, it is minus the degree. Because if your polynomial has positive degree, then it has pole at infinity. And the order of the pole is exactly the degree of this polynomial. But when you consider the vanishing order, then the order of a pole is taken with the minus sign. That is v of infinity at q is minus the degree of q. And since you have already minus here, you get plus degree of q plus degree of q. And the same reasoning applies to p. So minus degree of p. Thank you. So this is an example of evaluation corresponding to a prime divisor on a normal variety. In this case, this is just projective line. Let me also give you another exercise. Exercise 2. Suppose your variety X is quasi-affine. Then prove that every map I will denote it by the same letter V, defined on the algebra of regular functions on X, well, without zero, with values in Q, satisfying the properties 1, 2, and 3, in the definition of the valuation, and such that the image of this map V is contained in a cyclic subgroup of Q. Every such map satisfying these first three conditions without any change, and of course you cannot have this fourth condition because the image of the map V is in this case not a subgroup, because you cannot divide functions. So this guy k of x without zero is not a multiplicative group, it is a semigroup. So the image of V is again a semigroup in Q. But now the assumption, the property 4 is replaced with a different property, that the image of V is contained in a cyclic subgroup of Q. So prove that every such map uniquely extends to evaluation of the function field. In other words, if you want to define the evaluation, if you want to define evaluation of a function field on a quasi-affine variety, it suffices to define it on the coordinate algebra, on the algebra of regular functions, with all these properties, of course. So this is also an easy exercise, and let me stop the first half of my lecture at this point. So if you have any questions, then please go ahead. Any questions so far? Well, actually, this is again somewhat standard material from algebraic geometry and commutative algebra. I just give you details because I define basic concepts like valuation in a special way, which will be convenient for me in my lectures. That's why I define these things in detail for you. But of course, it is nothing special in what I'm just telling you about. So the notion of evaluation, you can consult, for instance, a book of Zariski Samuel in commutative algebra or other textbooks. It is explained in many sources. Well, so are there any questions so far? It seems that so far there are no questions. Then I'll mute my microphone, but I'm still here.
Oh,
so you can. Yeah, yes. Yeah, please.
Okay. Early question. Well, too early. I don't think it is suitable to ask here. I have to.
You mean what is not suitable? Could you please say this?
Well, this is a question from the first course because I think when you define when you prove the the section space of a homogeneous line bundle is isomorphic to a homomorphism of H modules, your action of a group on the function is not like what you write today. Well, I think in that course, in this course, an element B acting on F is by
you mean this formula? We are discussing this formula, right?
Yes. Well, I think in the first course you write B acting, the value of B acting on F at X is the value of X times B.
Well, I wrote something like this. Well, let me preserve the notation B for the acting element. I wrote something like this. So if you take a section S and if you act by some element B of the group on this section, then you get another section.
Not this section. Well, not about the action of group sections. I think it's better to write an email if I still have questions.
Yeah, because it concerns, I think, yes. So please write an email to me and explain your question in detail, because it concerns some of previous lectures. So I'm pretty sure that I didn't make any mistakes there, but everything is possible. So if you find something contradicting which I'm saying right now, then just point it out, we'll discuss. So please write an email to me. Okay. So, more questions? Then I'll mute my microphone, but I'm still here. Okay, so I think we can continue. Uh, so this definition of evaluation was very general, but now let's come back to the spherical case. So if X is spherical, then recall that we have an exact sequence of this form. 1 to k cross to the group of semi-invariant rational functions, B semi-invariant rational functions, to the weight lattice to 0. And suppose we are given a valuation V, valuation of the function field of X over constants. Then we can restrict this valuation on the group of B semi-invariant rational functions. So we get this map given by V, by the restriction of V, from this group to Q. This is a group homomorphism, still a group homomorphism. By the definition of evaluation which we have given, the constants map to 0. And this means that this map V given by the middle vertical arrow descends to a homomorphism from the lattice lambda x, from the weight lattice, to the additive group Q. So in other words, we get a linear function on the weight lattice. Let me denote these linear functions by V bar. So the valuation V restricted on the semigroup of B invariant rational functions factors through a linear function on the weight lattice. And here is a crucial lemma. It says that if your valuation is G invariant, a G invariant valuation, say V, is uniquely determined by this linear function. So essentially, this lemma says that a G invariant valuation, so G invariance is crucial here. A G invariant valuation is uniquely determined by its restriction to B semi-invariant rational functions. So it is evaluation of the whole function field, but it is uniquely determined by restriction to semi-invariant, B semi-invariant rational functions. And if it is so, then as it was explained here, of course, it is given just by this linear function on the weight lattice, because this guy goes to 0, always goes to 0. So this lemma is a bit technical. The proof will occupy some time. So let me start the proof.
So, Professor, every valuation can determine a linear function on lambda x on the lattice.
Yes, of course. In this construction, it is not essential that V is invariant. You just restrict V to B semi-invariant functions. And since constants go to 0, then you can push it down to the weight lattice to give this map, to get this map. So every valuation.
So what's the action of group on valuations?
Well, as usual, I mean, the group acts on functions, yeah? The group acts on X, and therefore the group acts on functions. And since it acts on functions, it acts on functions on functions. So valuation is a function defined on the set of functions. So the action is transferred to this set of as well. I can write explicitly. Well, if you like, I can write explicitly. Let me do it for you. So G acts on V, it is again a valuation whose value at F is the same as the value of V at G inverse F, as usual. And G invariant means that V of F is the same as V of GF for any G.
Okay, thanks.
Yes. Okay. Okay. So let's first prove the lemma in the quasi-affine case. So first consider quasi-affine case. If X is quasi-affine, then as it follows from my second exercise, yeah. So by exercise 2, which I leave you to solve, the evaluation V is uniquely determined by its restriction to the coordinate algebra of X, by its restriction to regular functions. So it suffices to consider the evaluation on this algebra of regular functions. And what is the regular of the algebra of regular functions on my spherical quasi-affine variety X? It decomposes as the direct sum of irreducible G submodules, and each irreducible submodule occurs up to an isomorphism only once. So it is a direct sum of subspaces, say kx, k of x sub lambda in parentheses, where each of these subspaces, so what is k of x sub lambda, it is a G-stable subspaces is isomorphic to the irreducible representation of highest weight lambda. Let us denote for convenience by, well, actually we already use this notation. F sub lambda is a B semi-invariant function in this space of weight lambda. This is just the highest weight vector in this G submodule. Highest weight vector. Okay. Now, so this is a decomposition. This is a canonical decomposition of the coordinate algebra of a spherical.
So,
yes.
So exercise 2 does not require X to be irreducible.
No. X is spherical. Spherical assumes irreducible. X is a spherical variety, which means that it contains an open orbit. I mean
exercise 2.
In exercise 2. Okay, in exercise 2. No, it is assumed irreducible because you are discussing function fields. You are discussing fields of rational functions. And it makes sense to speak about a field of rational functions only on an irreducible variety. So X is assumed irreducible, of course. Okay?
Okay.
Well, yeah. So we have this canonical decomposition of the coordinate algebra of X into the sum of irreducible submodules, which I will denote in this way. So it is not just an abstract irreducible G module. It is a submodule of K, in K of X of highest weight lambda. This is my notation. Now, a G invariant valuation, this G invariant valuation V, which we consider, gives us a G invariant filtration.
Oh, no.
Yeah.
No. No, go on.
Okay, so we have a G-invariant filtration. G-invariant filtration, decreasing filtration. On the coordinate algebra of X. That is, this K of X is the union of subspaces, which I denote like this: K of X greater or equal than C, where C ranges over rational numbers, but in fact, C ranges essentially ranges over the value group of Q, which is a cyclic subgroup, the value group of V, which is a cyclic subgroup of Q. So C ranges over some discrete subgroup on the rational line, which is just a cyclic subgroup generated by some maybe non-integer element. So essentially, this is this is like what we usually understand by filtration. So what is this? What is this subspace?
So the no less than C means the value is bigger than C, right?
Yes, exactly. Your guess is right. So let me write it explicitly: that this subspace K of X greater and equal than C is just nothing but the space of all functions f sitting in K of X, such that the value of V at f is greater or equal than C.
So
it is in
So we must need C is bigger than 0, otherwise the product of
No, it's okay. Everything is okay. I mean, it may take negative values as well, because you have this property. You have this property too. So this property too guarantees that this subset is indeed a subspace. Okay.
I mean, property 1 will violate.
There is no problem. There is no problem with property 1. So, by the way, I do not discuss the multiplicative property of this filtration.
If you only talk about the linear property, then
yes. But actually, the multiplicative property also holds. So the property 1 guarantees that when you multiply two terms in this filtration,
I think then the product of filtrations will sum up the index. I remember.
Okay. So we get this filtration, this descending, decreasing filtration, and this filtration is G-invariant because evaluation V is G-invariant because of this property here, because of this. So these subspaces are G-stable. Okay. Now, for any weight lambda, let me turn to the next page. For any weight lambda and for any C, we get the following. Either this filtration term K of X greater than C contains the irreducible summand corresponding to the highest weight lambda. Either this guy contains this guy entirely, or the intersection is 0. This is because both subspaces are G-invariant, G-stable, and this subspace is irreducible, is an irreducible G-submodule. So this intersection maybe can be either zero or coincide with the whole space here. That is, we have only two options. Either this guy contains this, or the intersection is zero. In other words, hence, our evaluation V takes a constant value on the whole subspace K of X sub lambda with zero removed. So it follows from the above two lines that the G invariant valuation V takes one and the same value on all non-zero vectors in this subspace K of X sub lambda. And then it follows that the filtration term K of X greater or equal than C is the sum of those irreducible subspaces, submodules, for which the valuation V takes a value greater than C, greater or equal than C on non-zero vectors in this submodule. But this value is the same as the value on the highest weight vector, the value on this f lambda. And the value of f lambda is given by this linear function on the weight lambda. So finally, we get that the filtration term is the sum of those irreducible submodules for which this value, V bar, evaluated at lambda, is greater or equal than C. Now it follows that for any non-zero regular function f, we can decompose this f with respect to this direct sum decomposition, with respect to this decomposition into irreducibles. We can decompose this f as a sum, say sum over I fi's, where each fi is a non-zero element, a non-zero vector in one of these irreducible submodules, say of highest weight lambda I. If we have such a decomposition, then it follows from the above observation that the value of f of V at the function f is just the minimum over all rational numbers C the minimum of all rational numbers C how to say, the minimum of rational numbers C such that the value of V is such, it's better to write like this, such that F sits in the filtration part K of X greater or equal than C. This is just by definition of the filtration, because when you want to evaluate your valuation at a given function, you just look in which filtration terms, to which filtration terms your function belong. And you take the minimum value, because this filtration is decreasing, you take the minimum value such that f belongs to this filtration term, to this filtration subspace. Okay? But this can be computed in view of this formula, and in view of this decomposition. This minimum can be computed as the minimum over all i's, the same i's as here, of values of f at this fi's, which are just the pairings of v bar and lambda i's. So this gives you an explicit formula for your invariant valuation on the coordinate algebra of your quasi-affine spherical variety X. And you see by this formula that indeed the valuation V is determined by this linear function V bar. Okay? This is an explicit formula expressing your V in terms of V bar. Okay, so we have done the quasi-affine case. And now what about the general case?
So is this decomposition finite? Always a finite sum?
Yes, of course, because it is a direct sum. I mean, excuse me.
I mean, it is a finite sum in the sum of
No, this sum is infinite, of course. This sum is infinite. This sum is infinite, but it is a direct sum. And this means that every element in here is decomposed as a finite sum of some elements in here.
Okay.
Okay. So let me turn to the general case.
Professor, I have a question.
Yes, please.
So we prove that. So here we say that.
Excuse me, there is some noise here. Maybe you should mute your microphone because I don't hear the question. So please, the one who is not asking the question, please mute the microphone. I don't hear. So please go ahead with your question. Go on.
So here we want to prove that V is uniquely determined by its restriction on its regular function.
Yeah.
Yes.
Yeah. This is exercise 2, which I put here. Yeah. In the quasi-affine case. So every map on the coordinate algebra uniquely extends to the valuation. So if you have a valuation, it is uniquely determined by its restriction on here. Okay?
So the key point of the lemma 1 is we want to prove that it is G invariant.
No, it is given. It is given that your valuation is G invariant. You are given a G invariant valuation, and you want to prove that if V is G invariant, then it is uniquely determined by V bar. Because you can define this function V bar for any valuation. In this construction, V needs not to be G invariant. But then V cannot be restored from V bar. So you may have one and the same V bar for different V's. But if V is G invariant, then it can be recovered from V bar. This is the point of this lemma.
So it means that every G invariant variation V on the rational function field just comes from V on the gamma X, right?
Every G invariant valuation comes from this V bar.
Yeah.
But I mean, you have also to describe those V bars which correspond to valuations. Not every linear function on lambda x defines your evaluation. This is not true. But I'm not discussing this issue. I am just saying that if you have a linear function V bar coming from a G invariant valuation V, then this V is unique. Okay?
Yeah.
Okay. Well, so far
I want to see the second part of the proof again.
The second part? You mean this?
Yes, I mean this.
So
why is the last equality correct?
Well, because you mean this one?
Yes, I mean this one.
Yeah. Well, because of this decomposition, because of this formula.
But we can have two different lambda I, such as lambda 1 and lambda 2, but their value at
yes. Yes. And so what? So I mean, you consider so. Mm-hmm.
So if the value of v bar at two different weight is the same, we cannot apply exercise 1. So why does the value?
But we take the minimum here. We take the minimum value. If you have two different values. Mm-hmm. So if you have two different lambda i's with different values of v bar, then this means that
with
they
the
both
same value of v bar.
With the same value, okay, with the same value, then okay, so the minimum is just equal to each of these values. So yes. And here also you have both subspaces in here. I mean this equality. So I claim that this equality stems from this decomposition.
Oh, I mean what you did now, huh? I know what you did now. Thanks.
Mm-hmm. Okay, good. So we handled the quasi-affine case. Now let's turn to the general case. And in the general case, of course, you can do the standard trick, which I called affinization on maybe on one of the previous lectures. So first, since valuations are birational invariant of our variety, we may replace the variety x with the open orbit. So we may assume that x is just y naught. It is just a spherical homogeneous space. And every homogeneous space can be embedded. Yes, yes.
I know why I feel strange. Well, shouldn't we apply the maximal number of C to the value of F?
No. I mean here everything is correct because the filtration is decreasing. The bigger is C, the smaller is the subspace.
Yes. So if you choose a minimum C, you can choose arbitrary low because if the value of F is greater than 0, then the C equals -1 -2 will always F will always belongs to kx greater than -1 -2. So there is no minimum.
Well, so you don't agree with this formula? I just don't get your point. Didn't get your point.
I mean, you should choose the largest C such that F belongs to kx greater than C. You can't choose the minimum.
Yeah. You are right. You are right. Thank you. Yeah, thank you. I mean here. Here you should put maximum. Yeah. This is what you just said, right? So when you increase C, your filtration subspace becomes smaller, and you want to trace the maximal possible value for which this filtration subspace still contains F. Yeah. And this will be exactly the C will be exactly the value at F.
Yes.
You are right. So here, yeah. Thank you so much for this correction. So here you have maximum, and but here, I mean here, when you have this decomposition, you have minimum. Okay. Yeah. Thank you. Now let me anyway turn to the general case. So as I said, in the general case, we may assume that the variety X is just homogeneous. just a homogeneous space, and each homogeneous space, as we know by Chevalier's theorem, can be embedded in the projectivization of a linear representation of G as the orbit of some point in this projective space. Let's write this. Okay. And now we take the affinization of this orbit. So we pass to the orbit of a bigger group. Let me denote it. It seems to me that I already used this notation. This y naught hat. Y naught hat is the orbit of the vector v under the group g hat. So this orbit is sitting in the vector space v, where g hat is the product of g and the multiplicative group of the field acting by scalars on v, by scalar multiplication on v. So we have this quasi-affine orbit in the vector space. This is actually just the punctured cone over y naught. So if you want to have the picture, so the picture is like this. So you have this y naught. It is an orbit in the projective space. And you have the cone of this orbit with 0 removed. So the punctured cone, excuse me, should draw this better, like this. The punctured cone over this orbit. And this is, I mean, this is my this is my y naught hat. This is y naught hat. Okay. Now let's consider. Let me turn to the next page. Let's consider the function field on this bigger orbit. Question?
Is this technique same as what we used 2 courses ago?
Yes. This is the same technique, but applied to a different problem. Yes, this affinization technique is always the same. So let's consider the function field on this conic orbit y naught hat, the field k of y naught hat. Of course, it contains the field of functions on k naught. Just because we have this projection map, we have the projection map from here to here. Projectivization, better to say, projectivization map from this orbit in a vector space to this orbit in the projective space. And this gives you the inverse inclusion of function fields. So this field is a subfield in here. And actually, this field is an extension, a simple extension of this field by adding a generator t, which is just any linear function on the vector space. So t is a linear function. When you want, so let me come back to the previous page. When you extend the function field on a projective variety to the function field on an affine cone, over this projective variety, you just add a linear function on the vector space. Add a function, a polynomial in projective coordinates of degree 1. You may just add one of the coordinate functions if you like. So it is a pure transcendental extension. This is a pure transcendental extension generated by this t, where t is a linear function on V. We may choose any. Let us choose B semi-invariant function, the highest weight vector in V star. Well, restricted, of course, restricted on this y naught hat. We view this function as a function not on the whole vector space here, but only on this subvariety. Okay? And now the point is to extend. Yes.
What do you mean by being invariant here?
B semi-invariant. The same. I mean, this being in parentheses means B semi-invariant linear function, B semi-invariant vector. Semi-invariant means that when you act by B, it is multiplied by a character. We know that in any representation of the group G, there exists a B semi-invariant vector, the highest weight vector. So we take one of these highest weight vectors. Okay. Now we may extend the evaluation V on here to the evaluation V hat, evaluation of this bigger function field, K of y naught hat over constants. Essentially, we have to define, so we know what are the values on this field. We want to define values on this field. It can be done in many ways, but maybe the simplest way here in our situation is to put V hat of t equal to 0. And if you have an arbitrary function f, which is a polynomial in t with coefficients in this smaller field, so if your f is a sum over case of fk times t to the k, this is belonging to the polynomial ring over this field k of y naught, the polynomial ring with the variable t. So for such f, you just define v hat of f to be the minimum of v of fk's over k. Okay? And if your function is not a polynomial in t, so in general, if your f is a ratio p over q, where
我这边没什么问题，那就是我们再补一个平视乘积，对吧？
Excuse me, could you please mute your microphone? Because I don't understand what you.
不，那只有讲过的人有啊。
Maybe I can ask Huhan to mute microphones of those who is not asking a question. Okay?
啊，对对对，我也是这个原则。那就把这个讲过的人谁讲的往上一交就算了。
To mute all microphones except mine, because there is some noise.
对对对。
I'm afraid that Huhan.
Well, I think that that student is calling a phone.
好的。
So
yeah, but I mean I'm just asking to mute microphones from the host of the conference should be able to mute all microphones except for the speaker's one. But it seems that Huhan doesn't hear us. Okay, anyway, let me again ask everyone to mute microphones if you are not asking a question. Let me finish. So we extend the valuation.
I have a question, Professor. How can we ensure that t is not identically 0, or why not?
We choose such a t. I mean, of course, we have to choose t, which is not identically 0. Yeah, sure. It is a matter of choice. But we can do it because
it cannot be. So if it is not 0, it cannot be identically 0, or why not? No,
I mean, you always can choose a function which is not identically 0 on why not. On why not hat, maybe better to say on why not hat, because t is a function on why not hat.
Yes.
You can always choose such.
So how can we choose such a function so that it is also of the highest weight?
Well, because I mean, again, because you may consider, let me write something here. You may consider the vanishing ideal of this subvariety why not hat in the coordinate algebra of V, okay? It is a proper G-stable ideal, and you can choose a G-stable complement to this ideal. So you can decompose this guy.
We use that G is reductive, I see.
Of course, yeah, of course, sure, of course, you use this. So you choose a G-stable complement, and you can choose, and actually, since the algebra V, K of V is generated by V star, so V star, the projection of V star to here is non-zero. So you can choose a highest weight vector in the image of V star projected onto here, okay? And then lifted by complete reducibility, lifted to V star. So this is by complete reducibility. But well, I'm still not able to finish this construction. Let me finally say that if your f is not a polynomial in T, it is a ratio of two polynomials, and then you can write it is a ratio of two polynomials, and then of course you define v hat of f to be the difference of v hat of p minus v hat of q. So this is how you extend your valuation v from the function field of y naught to the function field of the cone over y naught, to the function field of this y naught hat. And an exercise for you, it is, again, here I give some exercises because there are too many small technical details, but these exercises are easy. An exercise for you, exercise, I guess, 3, is that this v hat is indeed a valuation. Check that v hat is indeed, this map v hat defined above is indeed a valuation. Okay. By the way, it has a geometric meaning. So let me maybe speculate on this geometric meaning. If the valuation v corresponds to a divisor, to a prime divisor d, then v hat just corresponds to the cone over this prime divisor, to d hat. So let me show this on this picture. So if you have a divisor d in here,
so
and your valuation v
does not need G invariance, right?
No. So far not. You are right. So if V corresponded to a divisor D, of course, this is not our case, because in our case, Y naught is a single orbit and it has no G-stable divisors. But this construction doesn't use G invariants. So even if V were not G invariant, we could define this valuation V hat starting from V. So if V corresponded to D, then V hat would correspond to this cone over D, to this D hat. Okay, this is a geometric meaning of this construction V hat from B. And now I use the next lemma, lemma 2, which I will prove later on the next lecture. Lemma 2. Which says that actually any valuation of any valuation V, not necessarily G invariant, of the function field of x over k over constants can be approximated by a G invariant valuation. For any such valuation V, there exists a G invariant valuation, a G invariant valuation V tilde of the same field, such that for any rational function f, there exists an open subset in the group G with the following property. For any G small in U, for any G small in U, excuse me, I think I have to close this. Okay. The value of V at the shifted function GF equals the value of V tilde on F. So let's look again at this lemma. This lemma says that you can replace your V, your valuation V, which is maybe not G invariant. You can replace it by a G invariant valuation, V tilde, such that for a given function F, the values of most of its shifts will not change. So
the F belongs to the quotient of Kx over K.
No, I'm sorry, it is not the quotient. Yeah, you are right. Of course, you are right. I have to move it away. Is it okay now? Yeah, it should be like this. For any rational function on X, there exists an open subset in the group depending on F, of course. U depends on F. Such that for any element in this open subset, the value of V on the shifted function will be the same. And this will be the value of the invariant valuation, which is our replacement for V. So this is, you may call this approximation.
So what
lemma.
is our lemma 1? I think we are proving lemma 1 now, right?
Yes, right. But we use lemma 2, which we will prove later, in the proof of lemma 1. We didn't finish the proof of lemma 1. We use lemma 2 in the proof. And how do we use it? We apply lemma 2 to the valuation we had, which we constructed above. Because we started from a G invariant valuation V, and we lifted it to a bigger field. We lifted it to a valuation V hat of a bigger field. But this valuation V hat needs not to be invariant. We replace it by a G invariant valuation, so we get a G invariant valuation, not G invariant, G hat invariant valuation, because we apply it to the action of G hat on U naught hat. we get a G hat invariant valuation, say V tilde again, let me denote it as V tilde, of the function field of Y naught hat of this conical orbit over constants, such that the restriction of V tilde to the field of functions on Y naught coincides with V. So V tilde equals V on K of Y naught. This readily stems from the lemma because you see that lemma says that you can replace a given valuation, now V hat, with a G invariant valuation, V tilde, such that it will take the same value on all shifts of F under general elements of the group. So if you take an element G be sufficiently general in some open subset, then these values will be the same. Here you can also put G here, because V tilde is G invariant. So you can put small g here and nothing changes. So V coincides with V tilde on all functions of this form for almost all elements G, all except for a smaller closed subset. And when you restrict on this field Y naught, when you restrict V hat to this smaller field, then you get your initial valuation, V, which is G invariant. So on the smaller field, this guy is already G invariant. And this value is the same as the value on F. So V of F coincides with V tilde of F. So this is what I have said here. V tilde equals V on the smaller field. So we have to stop. We have to stop now because my time is over. We didn't yet finish the proof of the lemma. It still will take maybe 5-10 minutes to finish the proof. But let me summarize what we have done. So we have proved this lemma in the quasi-affine case. And we started the reduction of the general case to the quasi-affine case. What we did, we extended a given G invariant valuation on the quasi-projective on the quasi-projective spherical homogeneous variety. We extended it to a G invariant valuation on the quasi-affine spherical homogeneous variety. So we had evaluation V here, and we extended it to evaluation V tilde here, which is still invariant, because we use this lemma to modify this V hat, which we initially had, which was our initial extension. We modified this V hat to V tilde, which is yet another extension of V, but now V tilde is G hat invariant. So we extended to a G hat invariant, to an invariant valuation on a quasi-affine variety here. And now I'm going to apply the quasi-affine case and deduce the statement for the general case. But details will appear on the next lecture on Monday, and now I'll stop. So thank you. And if you still have questions, then please ask your questions.
Well, first I want to look at the last page about the second lemma.
Okay. So this is the second lemma, which we didn't prove yet.
So will the next course reformulate this lemma?
You want me to reformulate?
I mean, the next course we will write the lemma first and prove it, not directly go to the proof.
The next step will be to prove lemma 1, to finish the proof of lemma 1 using lemma 2. We already used lemma 2 on this line, yeah? Next we finish the proof of lemma 1, and after that we'll prove lemma 2. Okay?
What? So apply lemma 2 to V hat will not be stated in the next course, right?
No, I mean we already applied this lemma here. So I just formulated this lemma 2 in this generality because it may be useful in other questions. So this lemma says that for any G invariant, for any valuation on any spherical variety, on the function field of any spherical variety, there exists a G invariant valuation on the same of the same function field, which approximates your given valuation V in this sense. So this lemma may be called an approximation lemma. Maybe I will use this name just for reference. Let me write it here. Approximation.
I mean, Professor, we are constructing a G invariant valuation from the linear function, right?
No, we are not. We are recovering it from a linear function.
Yes, we are recovering it from a linear function, but I think applying lemma 2 to V hat is just like the opposite. We already have a G invariant valuation, and we apply this to.
No, I mean we have a G invariant valuation. We have a linear function corresponding to this valuation, but we do not know that this valuation is uniquely determined by this linear function. We want to recover the valuation.
So the lemma 1 is not saying that any linear function corresponds to a G invariant.
Of course not. Of course not. And this is even not true. In the next lecture, we will describe explicitly which linear functions correspond to G invariant valuations. These are not all linear functions. It is an explicit subset in all linear functions. So we shall describe.
So this means any linear functions gained from any linear function deduced from a G invariant value, deduced from a valuation.
From G invariant valuation.
You first say that any valuation determined a linear function. And the lemma 1 states that the linear functions determined by G invariant evaluation
let me repeat again. Let me repeat again what I'm claiming. So the first claim, which is more or less obvious, is that to any valuation you can associate a linear function just by restricting this valuation to this semi-invariant subgroup.
Yes,
yeah,
I know this.
So the correspondence from V to V bar works for all V. I am not discussing which kind of V bars we get from arbitrary evaluations. What I'm interested in, I'm interested in which kind of V bars we get from G invariant valuations. And this I will describe on the next lecture. I will describe the set of those V bars coming from G invariant valuations V. Okay? This will come on the next lecture. And today I am claiming, so this lemma 1 claims that if you are given two different G invariant valuations, then we have two different V bars. Okay? In other words, V can be recovered from V bar.
how can we have two different
so let me write it here for you. So if you have V1, V2, G invariant valuations and they are different, then V1 bar and V2 bar are different. This is what claims what lemma 1 claims. This is exactly the statement of lemma 1 in different words. Okay? And this is what we are proving. Okay? Is it clear?
I know. So I understand. I did not understand the lemma correctly.
Okay. So I just maybe
every linear function determine G invariant. Not the case.
Yeah.
Oh, and another question. Why is the function field of y naught hat is constructed by adding a linear function to the function field?
Well, I mean, it is just some standard projective geometry. So when you have a projective variety or quasi-projective variety, this doesn't matter because we are speaking about rational functions. You can always take the closure.
I'm asking only one thing. Is y naught hat isomorphic to y naught times the affine line, or not?
Birationally, it is birationally isomorphic.
Oh, so the function field is the same.
Yeah. It is not isomorphic globally, but it is birationally isomorphic, of course.
Birationally isomorphic to y naught times the product of y naught and affine line, right? Yes.
And this is a geometric explanation.
So the extra coordinate of the affine line is mapped to a linear function, right?
Yes, of course. Okay.
Last question.
Please.
How can we show that the function field of y naught is contained in the function field of y naught hat in this graph?
Well, I mean, again, by basic algebraic geometry, you have this map, right? From the cone to the projective variety. Yeah.
So you have
projectivity. Yes. You have the pullback map for functions, exactly.
Yes. I know.
Professor,
I have
a question about
please
the last page.
So
the last one page.
The last page.
So here lemma 2 says that we exist an open subset of G, yes, and we have all those G in U, such that we have this inequality. So how can we apply this to the lemma 1 here? Where is the U?
So we apply this lemma. So this lemma is about evaluation on the function field of a G variety X. Yeah. Now we take so X here is a G variety, a variety equipped with an action of a reductive group G. Now what you do, you just take a reductive group G hat here, and your X will be Y naught hat, and your V will be V hat. So we apply lemma 2 to this situation, okay?
Yeah.
And then the claim is that you may replace this V hat with another invariant valuation, V tilde, such that this property will hold. So everywhere here you just when you apply to v hat, then in the formulation of the lemma, you replace x with y naught hat, and yeah, and that's all. So you get this v tilde. It is already a g hat invariant valuation of this function field. Yeah.
Yeah.
And now I claim that v tilde coincides with v on this smaller subfield. This is because if you take your f from this smaller sub, here I should also take v hat. Yeah. If you take your f from this smaller subfield, so if you take, let me again just modify what is written here. If you take f from the smaller subfield, so if you remove hat here, okay, if you remove hat here, then actually on this smaller subfield, your v hat, the valuation v hat, which you approximate by v tilde, your valuation v hat will coincide with v, what you started with, because v hat was an extension of v to a bigger field. And when you come back to a smaller field, you get v itself. So if f is from the smaller field, then here you have just v, okay? And you have this statement. But v, the valuation v, was already G invariant, just by construction. It was already invariant, by assumption, it was already invariant. So this means that v of G f is the same as v of f. And we get that for f in the smaller field, v and v tilde have the same, take the same value. This is what is written here. V tilde equals v on the smaller field. Okay?
Clear.
Did I answer your question?
Yes. Thank you.
Okay, great.
Well, the modified lemma 2, the second line of the modified lemma 2 should be y naught hat.
Well, in general, yes, in general, yes. But when I explain this last line here, I mean when I explain this equality, that v tilde coincides with v on this smaller field, I take f from the smaller field. Okay.
From this field is contained in the larger field. Yeah, I know that. About the last question and the left up corner. Well, the decomposition.
The left upper corner. You mean this here?
The right up corner. Sorry.
Okay, here.
Yes. So the decomposition of the regular functions on V into the vanishing ideal of y naught hat and another G invariant model M, right?
Yeah.
Well, M is not zero. But how can we ensure that there is a linear function in M? Well,
actually, M is identified. M is identified. Let me write it here. M is identified with the coordinate algebra of y naught hat, because M is identified with the quotient of this coordinate algebra modulo the vanishing ideal, and this is exactly the coordinate algebra on the subvariety on y naught hat.
Oh, sorry.
So
there
since
exists a linear function, right?
Yeah, I mean just because this projection map from here to here is just a surjective homomorphism of algebras. And this algebra, K of V, is generated by V star. So the generating set of this algebra maps onto the generating set of this algebra. In particular, it is non-zero.
Yes, I know.
Okay.
So why it is direct sum here?
This is because of complete reducibility. So representations of reductive groups are completely reducible. This means that given any G-stable subspace, you can always find a G-stable complementary subspace. So this vanishing ideal is G-stable because it is an ideal of a G-stable subvariety. It is an orbit. Well, G-hat stable, better to say, because here the acting group is G-hat, but it is still reductive. So this ideal is stable under the reductive group, and therefore you can find a complementary subspace in here. Okay?
So here the V star arrow to n means
this arrow is just a projection map because this guy, this star, is contained in here. And you have a projection map from K of V to M, which is identified with the factorization by this vanishing ideal. Okay.
yes.
Good.
I have one last question. In lemma 2, do we need the open set U containing the identity element?
Not necessarily. It may not contain identity element. It is just an open subset. Yeah, the point is that here U may not contain identity. Otherwise, V just would coincide with V tilde. And this means that your initial V was already invariant. So there is nothing to prove that. Indeed, this U may not contain identity. We shall see where this U comes from in the proof of lemma 2, of course. But so far, it is just a statement. Okay. So more questions, comments?
Well, and the last line, well, how did the two valuation agree on KY0? I mean, if the open set does not contain the identity element.
Just because, yeah, just because. So actually, everything is written here. Just because.
I know. Since V is G invariant already.
Exactly, absolutely, yeah. Okay. More questions? Well, thank you for your questions. In fact, at least they show that you listen to the lecture actively. You just try to think, and this is very good. And also thank you for, I think I should thank Lejean for this correction in the quasi-affine case, where you told me that it was a good remark that here I should replace minimum with maximum. Of course, you are right. I'm sorry for this confusion, and thank you for correcting me. So thank you all for your patience, for your attentive listening to the lecture. And if you have no more questions, then maybe I shall stop sharing. And also, as we discussed during the lecture, if you still have questions, even concerning some previous lectures, some very first lectures, then do not hesitate to write on email. The email address, my email address, is in the chat. And also, I think that it is in the notes of my very first lecture. So please write me on email and please ask your questions in more details with formula, with whatever. And also, I expect you you are very welcome to send me solutions of exercises. So far, there were already enough exercises during the lectures, and I hope that you will solve them. At least if you need credit for this course, then you should solve exercises, and I should check your solutions, because you should send me written solutions and I should check it, because as we agreed, the final grade will take into account your homework, so solving exercises. So please solve the exercises and send me your written solutions. I will check and reply. Okay, so if there are no more questions, then goodbye, all of you. Thank you, and see you next Monday. Bye bye.